and we'll start with, I think we'll start with 12, okay? And I've been trying really hard, and I just haven't been able to figure out a way to get Sketchpad to do this. And I apologize. You're going to have to deal with some bad drawings on my part. I will try my best, but they're not going to be great. So the first quadrant region bound by the graphs y equals root x and y equals x squared. I have a pretty good idea of what that's going to look like. Something like that, I think. And where do they intersect? 1 comma what? 1 comma 1 and 0 comma 0. So this is the region that's bound by those graphs. And we're going to take it and we're going to revolve it, rotate it around the x-axis and then the y-axis. So we're going to go around the x-axis first. And this time, when we rotate around the x-axis, we're going to get a very interesting shape. You want to take a shot at what that shape's going to look like? All right, so a bowl with a hollowed out, yeah, with the funnel. Didn't you say funnel? So it's actually going to be something that's missing something. So I agree that on the outside it's probably going to look a bowl, and then Betsy's saying, yeah, but in the middle we're going to be missing like... So I don't know. So let's see. It's going to look something like that on the outside. Then on the inside... Now this is really hard to draw. It's going to look something like that on the inside. So you're going to be sort of missing the funnel from the inside. So I don't know, like... Uh-huh. Of course. You run across those all the time. I don't know, like a daisy? Nah, not really. A tulip? Sorry, I should have deferred to my flower. How'd you do?
She won.
Oh, congratulations.
They got third place.
That's awesome, though. It's really cool.
Did you read her email? She was like, my architect.
All right. Now, because we're going around the x-axis, you can probably tell me right off the bat, dx's or dy's? Dx. And that means we're going to be slicing it this way. All right, so let's take a look at what it looks like when I slice it. It's going to look like...
Wait, but is that still doing it on the y-axis, the shape?
Say again?
Did you rotate it on the y-axis?
This is 2 questions. I'm just doing that right now.
So this isn't like do it on... Like,
No, it's 2 questions. So, how'd I do with my picture here? So, Jack said it's going to be a couple things. What is it this time? It's like a donut, a big radius with a little hole. Like, so it's 2 things, Jack, and it does. A lot of people like to call them donuts. We can also call them washers. And by washers, we mean not like a washer and dryer, but like a nut and bolt and a washer. All right, because that's what this looks like, a little washer. So we have a difference between discs, which are solid, and washers, which have a hole in the middle. But actually, this is just the difference of 2 discs, right? Take the big disc and subtract the little disc. Yeah. As a matter of fact, if you go back, Asa was saying a couple days ago when we were doing areas, really what we could do is we could find the volume of the whole thing, Derek's bowl, and subtract the volume of Betsy's funnel. We can do that either in 2 separate steps or in 1 step. Let's see, in 2 separate steps it would be pi r squared dx minus pi r squared dx from 0 to 1 and from 0 to 1. And in this case, the big radius, the radius of the big circle is what? What kind of value is that? It's a y value. And we know this case, that's the root x one, I think, is in blue.
Yeah.
So we get root x squared dx. And then, whoops, that's not equals, that's minus. Minus pi from 0 to 1 of this other r squared, which we'll do in green. That's this r. But that's also what kind of value? Y. But it's a different y. It's x squared squared dx.
Wait, can you stop for a second?
Is that just like colonized?
Yeah, very, very similar to that.
But is it, does it always
Bigger,
Uh-huh.
big minus,
We could have written it like root x squared minus x squared squared dx. We could have just written it as 1. And you actually learned this in geometry. Washers have a really special name. Do you remember what we would call? Circle minus a circle. I'm sure you giggled when we did it in geometry.
Oh my god. I feel like I remember this.
I'm sure you do. It's an annulus. Right? That's what we call it, an annulus.
It's like a ring.
It is a ring. It's exactly like a ring. Oh, come on. We talked about it, right? I'm sure you talked about it. So one way of thinking about this is when you have a washer, instead of pi r squared, it's pi big R squared minus little r squared dx or dy. It's just the difference of two.
Mm-hmm.
All right? So that's what we're going to do today. All right? So now your list of questions has to start with, is it a disk or a washer? dy or dx? From where to where? What are my r values, x's or y's? Okay? Yeah. It's a long dialogue that you have to have, and you'll get better and better at doing it by doing more and more. Do you want to do this one, or do you feel like, whoops, that's from 0 to 1. Do you feel like that's okay, or should we keep doing it to get an answer? All right. Go around the y-axis now? Okay. I have a question. Do you think the volume's going to be the same or different when we go around the y-axis?
different. We're actually, I think it's different. Yeah, it is different because it's wider. The inside is wider than
I don't know.
Or maybe not. Actually, no, it's
There's
different.
the fact that they're like you have the same.
Well, it depends on the area between. Depends on the area between the intersections.
Yeah, and I guess because what do I know about both of these functions?
Like
There's a very special relationship.
They're like the.
Not quite
what
the
do they
word.
call those? Inversions of each other. Like that's the inverted function of each.
Yeah, the inverse. It's the inverse of each function. Okay, because both of these functions are inverses, I'd actually say that the volumes are going to be exactly the same. Okay, so let's do it. So the first question I asked, disks or washers? Does it have a hole in the middle or is it solid? What do you say?
Washer.
Washers. dx's or dy's? Am I spinning around the x-axis or the y-axis? Y. So dy. So, say again?
Like if you look at it and
You said the
imagine
visualizer.
it spinning, you see like how there's like a space between the y-axis and the thing. Yeah, it's right there.
That's
Like if
how
you
you know.
You really got visual.
So basically, because it's concavity, does it have concavity?
Well,
well,
so,
because there's a space. So like if it was spinning, it would be empty in the middle. Like think about that spinning. It would be empty in the middle.
so if you're, I understand and I agree with what Betsy's saying. Like there's this idea that there's empty space between the function and the y or x axis. If we shaded this all the way down to the x-axis or all the way down to the y-axis, then there wouldn't be a hole in it. Okay? Is that all right? So the last thing I have to ask is, well, not the last, but where am I stacking these? I'm stacking them along the y-axis from where to where? From 0 to 1. So look, we just ask ourselves a set of preliminary questions, and we're already like halfway there in terms of the setup. And I would say the setup is at least halfway there to the final answer. Like the setup's probably the most important piece. So, in this case, I have two r's. I have a big R, which is the radius of the big one, and then I have this little tiny r, which is the radius of the smaller circle. So, what kind of values are those radii? Are they horizontal or vertical values? Horizontal. So as soon as I say horizontal, I know that they are x's. All right, so let's see. The big radius, let's see, which function does that correspond to? That corresponds to x squared. So the big radius is equal to x, and I know y is equal to x squared, so Gabby says exactly that's equal to square root of y. All right, so I get root y quantity squared. So the big radius.
You just said everything equals to each other. Big radius is going to equal y or equals x, and x is going to equal square root of y. So r also equals square root of y.
So the big radius is equal to an x value for this function. Well, this function is the function y equals x squared. Y equals x squared is the same as x equals root y. So since r is equal to x and x is equal to root y, the big radius must be equal to root y. Okay. I'm going to do the same thing with the little radius. All right. Oops. So here's the little, oh my gosh, why is that one so much thicker? Yeah, but the blue one, I did blue thick too. I don't know what's going on. Okay. So there's the little r. And let's see, little r is also an x value, but in this case, Gabby, what's x equal to? All right, so y is equal to root x, or x is equal to y squared. So I get y squared squared. And check this out. It should come as no surprise that these two answers are actually the same, right? One is just root x squared minus x squared squared dx. The other is root y squared minus y squared squared dy. The same exact setup, just using different variables. I'll try. It's not going to be as good, and it's definitely not the same shape. But with Sketchpad, if you, let's see, if we take like this, and this just happens to be root x, so this is a different problem, but it's just trying to help you visualize, and we spin it around the line y equals 3. So this is not the x-axis. It's a line other than the x-axis. And we revolve that. We get this sort of shape, right? And then if I stop revolving it, and then I can show you that washer, you can see how, in this case, the outer radius is always the same, but the inner radius changes, right?
Look for the change in x.
Mm-hmm. All right, so not the problem we're doing, but just trying to help you understand and visualize what we're talking about when we say washers. Is that okay? It's hard. I really do think visualizing some of these problems is very challenging. I've been doing it for a while, and I actually I like geometry, so I think it's helpful. If you weren't a huge fan of geometry and you just are starting out learning this, it's really hard to figure out, what the shape is. And if you can't figure out what the shape is, it's hard to sort of figure out how to go about doing it. There are ways of memorizing, though, through it, so you don't have to understand it all conceptually. Do you want to ask a question? We're going to do another one, but do you want to ask a question? I'll take that as a no. All right.
Why do you assume that every one is going to be the derivative of a cone?
Say that again. I don't think I'm assuming that. What was your?
It seems like, doesn't a cone have to have perfectly straight sides? Like it can't really be curved.
Are you talking about a cylinder? Is that what you mean?
I'm talking about a cone, like.
I don't think I'm assuming anything's going to be a cone.
But like when you set up everything, whether it looks like the perfect cone or not, it always has the R squared.
So,
that's the
right, it has.
When it spins around the x-axis, it makes it
Oh, okay.
All right, so it has nothing to do with a cone. Although we looked at the volume of a cone on Friday and we saw that adding it up as circles is the same as doing the cone. But the important thing is that whenever we do spin it around the x or y axis, we're always going to get either a circle or a washer, in this case, a disc or a washer.
Also, the cone, think of it as pi, or like the R squared is like I get what he's saying. Like, isn't it like the area under the cone is like little R squared?
No, pi r squared dx, that represents the volume of pi r squared h of a cylinder. And what we're doing is we're adding up lots and lots of these little cylinders. That's what it is.
Oh, okay.
All of these little...
So it has nothing to do with the big shape itself?
No. It's just that we're adding up tons and tons of tiny little cylinders. Now this cylinder happens to have a hole in the middle.
Yeah.
And you could see if we added up, if we broke this up into like 5 cylinders, it would have very chunky sides, right?
Yeah.
But the idea is the definite integral adds up an infinite number of super thin cylinders, and that allows us what to do it.
All right. Thanks.
Is that okay? Okay. All right. Classwork, and I think we're going to jump down to 15. And I think I'd like to look at maybe C or D, because that's hard. All right. Nope, that did not work. Let me try that again. All right, so all along we've been rotating around either the X or Y axis, but you can revolve around any axis you want. And so now we're going to do things parallel. So I think I'm going to start with C. And it says the region down by the parabola, y equals x squared, and the line, y equals 4. Where do they intersect?
460.
Try again. Say again? 2, comma 4.
Oh.
You're thinking x was 4. All right, so this is what I'm talking about, that region. And I want to spin it around the line y equals 5. Well, that's this line right up here.
What grade is that?
What's that going to look like?
a washer.
I agreed.
It's an empty piece. It's gonna have like an empty,
An empty,
cylinder.
yeah, an empty cylinder.
It's gonna look like a tire.
How about,
Okay, you know those marshmallow candy things?
It would look
Those,
like a bowl, but like with an empty lid.
those coconut ones that are pink or whatnot that look like these
Oh,
little
snowball.
snowballs. Except a snowball with like a cylinder like cut out of it.
okay.
Or it's like the piece where you put on a tire.
It'll have a
You know?
complete. We don't have a. It'll have a complete hole through it. Right?
Yeah, it definitely will. It'll have this cylinder cut out of it. How about like one of those umbrella stands that you put on your back porch to hold up the not like an umbrella like the rain umbrella, but the big umbrellas on your back porch. You have to put them in that stand.
I like my picture.
Right. Okay. So Betsy actually starts us off by saying, "Hey, discs are washers." It's a washer. It has a hole in the middle. All right. Now, dx.
You know how we're talking about like there's empty space? Is that just because there's empty space between 4 and 5?
Yep. Exactly. Okay. If we were to revolve this region around the x-axis, there would also be empty space here because there's empty space between the function and the x-axis.
So if the lines are parallel, you know it's going to be a cylinder.
That's going to be removed.
Yeah.
Yeah, I get. That's an.
And if it's like curved, you know it's going to be like a type of funnel.
I guess. I mean,
Like really basic.
yeah. Sure. Yes. I'll take it. DXs or DYs?
Yeah.
Why?
Yeah.
Why? It's going around the Y
No,
equals
Oh,
Y.
no, I'm not bad. No, use dx. The dx will tell you
It
why.
would be it's parallel to the.
All right.
To the
Let's take a look at one of these
The
washers.
radius is R and y for the
yeah, R equals Y.
Yeah, so it's dx's.
So look, this washer has a very, very thin height. Is that a vertical or a horizontal?
Horizontal.
That's a horizontal. That's a dx. Now, here's a little confusion. Y equals 5 is not the y-axis. So if you're a memorizer and you think every time I spin around the y-axis is dy,
Yeah, but it's parallel to the X.
that's it. Say it again, Betsy.
Parallel to the X.
Y equals 5 is parallel to the x-axis.
So does it even matter
So-
if it's like y equals 5? Like, does it really make a difference when we do?
Well, it's going to. Watch. So I want to make sure we set this up. Along the x-axis, where are we stacking these to and from?
From 0 to 4.
Hmm,
2.
2, because it's an x value. All right, now, this is where it gets a little hard, and I'm a little anxious because I think the bell is going to ring shortly, so I'm going to try. Now, I'm going to actually start with my little radius because Gabby made a very interesting observation. The little radius is from this axis.
So it should always equal 1.
It's always 1. It's always 1 because Gabby said there's going to be a cylinder removed from the middle. All right? Now, the big radius is hard.
Wait, why is it 1?
Well, this is the line y equals 5, right? This is the line y equals 4. So the radius of this inside piece is always 1. The cylinder that we remove, that radius is always 1.
Why isn't it 1?
Because we're spinning it around, right? So when we flip it over, right, it's going to be double that. Is that okay? All right, the big radius is hard, and this is where I'm a little anxious. Okay, so, look. I want to know what this big radius is, but that's not something I know. What do you got, Jack?
Couldn't you find out so like y equals x squared, but you know that's minus 1? So wouldn't it be like x squared minus 1?
All right, let's hold on.
Take that in for r, so big R.
I know that this red value is y equals x squared. I know that the r value that I'm looking for is the green. And Jack, you're not totally right, but if I use what you said, I know what this value is always. That value is always 5.
Let's do 5 minus.
5 minus
5 minus
x squared. That's exactly it. And that's hard.
probably.
So the radius is 5 minus x squared, quantity squared. As a matter of fact, do you know where this 1 really came from that Gabby said? That 1 is really 5 minus 4. It's the whole thing, 5 minus 4, which is what we don't want, is 1. Just like here, the big radius, the green, is 5, the whole thing, minus y equals x squared, what we don't want. This is, Asa, sort of back to your area conjecture. It's everything that, the whole thing minus what we don't want leaves us with what we want. And here's the thing. This is considered hard. No.
Oh my gosh.
You can foil this out if you want or whatever. All right. But I want to say this. Revolving around an axis that is not the x or y axis, that's as hard as it gets. So I think what we did is we reinforced discs today. We learned washers today, and then we extended washers to really hard problems. So we're going to spend today and tomorrow going over discs and washers, and then doing more problems where it's either around the x or y axis, which you'll like, or around another axis, which makes it sort of hard. All right? Do you want to ask a question?
Yeah.
All right. Try doing what you can tonight. Certainly come in with questions tomorrow, and I'd say by the end of tomorrow, we really want to make sure we're feeling more confident than I think we were today.